So let's just do this last activity, which is numbered 314 in the textbook, but is numbered 3112 in your activity sheets. And just do the first portion of part B. So just verify that this function, t of f, is 3x times f applied to x squared. So we're going to feed x squared into the function and then multiply the result of that by 3x. Prove that that respects the addition operation. So let's take 10 minutes to have you write up your just your portion of the proof that t of f plus g is equal to t of f plus t of g. The task was to prove that this function t, which takes a function f and evaluates it with an argument of x squared and then multiplies the result by 3x, we wanted to show that this t was a linear transformation. And so to show that this t was a linear transformation, we just followed the directions, right? Show that t of a sum is the same as the sum of the t's, and that t of a scalar multiple is a scalar multiple of the t's. And I want to just quickly spotlight the work that Team 2 did on this one, because they endeavored to write out that sort of 5-step proof. We claim that this transformation is linear. We'll prove by showing that the following conditions are true for all functions, that t of f1 plus f2 is t of f1 plus t of f2, and that c times t of f is the same as t of c of f. And so really where the rubber all met the road was in these computations here in the middle, that t of a sum f1 plus f2 is 3x squared times the function f1 plus f2 evaluated at x squared, which by definition of adding functions is f1 applied to x squared plus f2 applied to x squared. But then 3x squared times that sum distributes, because regular multiplication of real numbers distributes across addition. So 3x squared times f1 of x squared plus 3x squared times f2 of x squared, that's the same as t of f1 plus t of f2. So notice something that I particularly like about the way that this proof was structured is that they've worked from one side of this equality that they're trying to establish over to the other side, rather than trying to do work on both sides and then argue that both sides are equal. So this looks really nice. Same thing for t of a constant times f, that we get 3x squared times a constant times f of x squared, and that constant can pull out just because of the associativity and commutativity of multiplication of real numbers. So this function t here does satisfy the criteria to be a linear transformation. And again, that is all that's required for a function to be a linear transformation, is that it respects sums and it respects scalar multiplication. And geometrically speaking, just to wrap things up for this section, respecting sums means that if I take two vectors v and w in my domain and I look at the image of their sum, the image of their sum is going to be the sum of the images in the codomain. So geometrically that means that this parallelogram that I start with in the domain, it's a parallelogram because that's how we geometrically add vectors to one another. I get a parallelogram spanned by v and w, and the images of v and w and their sum also span a parallelogram in the codomain. So what we're going to see after our break is what's going to happen if I have linear transformations that maybe don't do everything that we would want a linear transformation to do. Let's say I want to take this cat face and just squish it out completely, so that now the images of all of my vectors don't seem like they explore the entirety of R2 anymore. And that there are some vectors, for example, it looks like this vector v plus w is one of them, which in the codomain actually ends up landing on the zero vector, so that there's more than one solution to which vector from the domain ends up mapping to the zero vector in the codomain. So those questions are questions about the image and the kernel of linear transformation. So that's what we're going to talk about after the break. And then after we've gotten a taste of those, we'll do our standard matrix computational portion of the discussion today. So let's take 5 minutes and then we'll see that when we come back.